Understanding how you determine whether or not a particular variable is positive or negative is a really important thing to have in your toolbox. And so here I have listed all the situations in which the different variables are either positive or negative. So for the focal length, well, if you have a convex lens, we assume that that is a positive focal length. Concave lenses then are negative. And so just to remind you, convex means that they're bending out like that, and that's essentially a converging lens. It's also sometimes called a positive lens, simply because the focal length is positive. Concave, well, here's how I always remember concave. Concave, it's kind of like a cave opening. In other words, it goes in like a cave does. And so this has a negative focal length. It's also sometimes called a diverging lens or a negative lens. Now, in terms of object distances, we're choosing a convention in which objects to the left of the lens are positive and images to the right are positive. Once we've set these two things, that determines the rest of our signs. So, any object that is on this side has a positive SO. And we're measuring from the lens. Actually, we're measuring from the center of the lens. Since we're dealing with thin lenses, all of our distances are going to be measured from the center line of the lens. Image distances then, anything to the right is going to be a positive image. And so the simplest way to think of this is if you have a converging lens and you have your object outside of the focal length, then you end up with positive object, positive image. Now in terms of the heights, the height is measured from the optical axis. That optical axis is essentially the line of symmetry that goes through the center of your optical system. And so any points that are above the optical axis are going to have a positive height. Any points that are below, such as over here on the image, are going to have a negative height. Let's just walk through a couple more examples. So in this example here, we have a virtual image formed behind the lens. Because this image right here is to the left of the lens, this corresponds to a negative image distance. We still have a positive object distance and a positive object height, but we also have a positive image height. And so the value of y tells us whether or not that point is above or below the optical axis. So here we have an example where I'm picking a point that is below the optical axis. Because this image or this object extends over above and below, I can choose different points, and anything that's down here is going to be a negative height, anything above will be positive. And so if we choose a negative height here, we have a positive optical distance because positive object distance because the object is to the left of the lens. We have a positive image distance because the image is to the right. And then this is an inverted image, and so since we started off with a negative height for the object, we're going to have a positive height for the image. So I just kind of want to show you how our choice of object and image distance sign convention determines the other signs. So by assuming that objects to the left are positive and images to the right are positive, then we can determine what focal length and radii of curvature have to be, what their sign convention has to be. So we're going to use the fact that a converging lens creates a real image anytime the object is outside that focal length. In other words, SO is greater than F. So with our choice, this is our equation for the image distance coming from the thin lens equation, and so this is going to tell us whether or not when focal lengths need to be positive and when they need to be negative. And so for a converging lens, let's try and figure out what F needs to be. For a converging lens, when SO is greater than F, we know that SI also has to be greater than 0. So this right side of the equation has to be positive. So let's just try the wrong answer. Let's assume that for a converging lens, we have a negative F and see what this gives us. So we have SO times a negative f, and I'm just going to explicitly write in that minus sign. And then we have SO minus negative f. So this is going to be negative SOF over SO plus f. So that would give me a negative SI. What that means is this right here is not possible. F has to be greater than or equal to 0 for a converging lens, and f is less than or equal to 0 for a diverging lens. So now we can use the lensmaker's equation to see how the radii of curvature are defined in terms of their sign convention. So for our converging lens, we know that f has to be greater than 0. So let's go ahead and assume that we have an index of refraction of the lens greater than the surrounding region. That's a pretty reasonable thing to do. So in this case, it turns out that R1 has to be greater than 0. R2 has to be less than 0. And we can see that just from looking at this term right here. So if N2 is greater than N1, this part of the equation is greater than 0. In order for this term in parentheses to be positive, well, that means that R1 has to be positive and R2 has to be negative. And so that defines our sign convention. Now I want to point out this isn't the only sign convention. So what I want you to think about is what other sign conventions could there be? And if you made other choices, what would that mean in terms of your sign conventions for f and for the radii of curvature?